Hi, welcome back to the breadboard and the next in our series on motion control systems. What we're going to do today is start building a 3D printer. What I've decided to do is actually build two 3D printers. Why build one when you can build two, right? One is going to be very similar to, and I got inspired by, the Prusa I3 MKII, which has a flat bed that moves forward and backwards. This is sitting upright, but normally it's flat on the table, and has a gantry system that moves the Z-axis and left to right for the X-axis, the bed being the Y-axis. The other one we're going to build is going to be based on a Core XY, where the bed itself moves in the Z-axis but no other direction, so there are less moments of inertia with the big heavier objects. And the head sits on a Core XY platform that can move in the X and Y direction, that sits at the top of the build frame, and the build platform actually starts at the top and slowly works its way down. The main difference is the way that the heads are moved, of course, and the fact that you're moving the build platform down only and moving the heads in the XY direction. The head on the Core XY one is also driven by belts, and what we're going to do with this one initially is going to be using lead screws in all X, Y, and Z directions. Now, there's a lot of common parts in both of these systems, so we'll have a quick look at those in a second, but the first few videos are going to be focused on building this version. And the one based on the Prusa I3 MKII, we're going to look at seeing how to keep the price down. Perhaps instead of buying commercial products from your local industrial supply store or something like that, going to Banggood, eBay, AliExpress, etc., whichever one is your choice. I will provide links to components from Banggood. They're helping me out with some of my projects with things like spindles for the CNC, some couplings, linear rails, and things like that, and they're very good prices. So I will provide links to those parts as we come across them. The Core XY machine is going to be based on more commercial parts and is going to probably have a slightly bigger build volume. It's going to use aluminum extrusions, very similar to the ones in open builds, but these are going to be available from RS Components, AliExpress. At the end of the day, you can choose where you get them from, but because RS Components are sponsoring me for that build, then I will be linking to their components on their site. The one thing you get when you buy from somewhere like RS Components, of course, is a certain level of surety of the quality and consistency of the components, whereas when you buy from a lot of the other online Far East stores and things, there is some ambiguity about the quality that you'll get or the consistency of what you'll get. So, you've got less guarantee of getting it right first time, and you may have to change out a few bits and pieces and things. But anyway, we'll deal with those as we go through. Let's look at some of the components that are required for a 3D printer. First of all, the pieces that are common between the two. So I'm just going to adjust the camera and get you a little bit closer to this little setup I have here, and we'll just discuss a few of them. And I'll also be putting up some pictures sort of in this area as well, overlaid, so that you can see what I'm talking about where I don't have an item right here, right now. So what we're looking at in the main screen here is a 300 by 300 build platform. This is actually, it's got aluminum back to it, and it has like a PCB heated build heater bonded onto the front of it. You can see here, hot zone, do not touch, etc., etc. It can get up to probably well over 100 degrees centigrade for the build platform, and the actual platform itself is 330 wide by 330, but there's a certain area to allow you for mounting at the edges where it's not heated, so the actual volume is 300 by 300 on here. It's sitting on some various other pieces which I'll go to later on in the video, but this is actually showing it mounted on a plywood base, which is the first part of the construction. You could build something out of aluminum, you could use some solid wood, but plywood or MDF or something is very structurally sound and makes a good platform for building things. On the Prusa I3 MKIIs, they're using some structure based on steel rods that you can buy from the hardware store at 18 millimeter or 10 millimeter diameter or whatever they may be. I'll point you to the Prusa i3 Mark II website where they have all the build instructions and everything else, so you can see for yourself what the parts are. One of my intentions is that we will have a minimal amount of things that we have to actually manufacture ourselves in order to get this build complete. When you look at the Prusa i3, there are a lot of 3D printed components. Now, I have to say right at the beginning, no matter which way you go, there are some parts that you're going to have to build or make yourself. If you have a 3D printer already, then printing the parts to make an extruder, for example, is relatively straightforward. This is Bowden extruder. It's not all obviously hooked up yet, but it's got the stepper motor on it, the hobbed gear, and a bearing for driving the filament through up to the heated hot end. You'll need to have some kind of mechanism for mounting a hot end. So this is a E3D clone hot end that I got from Banggood, and I 3D printed a mount for it. Now, I haven't seen on any of the sites where they have a mount ready to go that you can buy, but because these things are available, this particular mount was designed by Tech2C. I'll provide a link to his site as well. The fan ducting at the bottom here, which takes for cooling the part, it directs the air from this fan down and onto the part that you're building, was actually a remake of one of Tech2C's ducts, but I think this one is slightly too long for the clone hot end, so I'm going to have to either adjust this or try and print maybe the original one and see if it fits better. But anyway, so this is one of the parts that it's a little more complex, so you may not want to make it yourself if you don't have a 3D printer, and just get one of the online services to provide it, or you can buy some of these plastic kits from Prusa directly and various other things. What I'm doing with this one is trying to make it with a universal mounting structure so that I could put a laser cutter or a small CNC router or a pen for plotting and various other things onto the head as and when I want. So I don't want to have something where we got linear bearings and the mount and everything else all in one unit. But either way, both printers are going to need to have a hot end, and the part cooling is not essential, but it would be a good idea to have it if you can do it. The other part you have to have are things like limit switches, so that when you home the machine, it will automatically know where the 0 points are. Now, you can do it manually, but having some low-cost limit switches or something like that is a good idea and makes things a lot more convenient and easy to do. One of the most important things with a 3D printer, aside from obviously having a really flat heat bed for working on, is to have a good controller. Now, I have two different controllers here. The first one is the one I'm going to use for this printer initially, which is based on an Arduino Mega. That's what's put on the back here, an Arduino Mega, and a standard, what is this called? It's a Ramps 1.4 board with little stepper drivers. These are Texas Instruments stepper drivers on this one, although there are a few different types available that can just plug in. And what this board does, it acts as an interface from the Arduino Mega to the stepper drivers and to things like an LCD control panel and stuff like that. Very inexpensive relative to more commercial products, and they work fairly well. And the software and the schematics and everything else are all open source. So if you wanted to make your own or do some variations on it or mess with the code, you could easily do that. The board that I'm going to use for the Core XY is this one, and this is an actual ST Micro evaluation reference board, and they have to have done it to completely control a 3D printer. Now, the difference is the one here can control up to 5 stepper motors. So you can see there's 5 boards plugged in here, and so you would have an X, a Y, and a Z, and the Z axis often will have 2 stepper motors driving it because it's lifting the weight up against gravity, and then you would have a stepper motor left for an extruder and perhaps 2 extruders if you're going to do something in color in your sharing, having 2 stepper motors for the Z-axis, for instance, on one driver. I actually prefer to have them separately driven, but you know, there's lots of builds where they actually have 2 stepper motors connected to the one driver. So there's 5 drivers in total on here, plus some inputs for things like limit switches, temperature sensors, etc., etc. The ST Micro board, it's a lot more expensive, but you've got a capacity way in excess of what the Ramps 1.4 board is. This actually will handle fans up to 20 amps each and a heated, very high-powered heated bed. All the stepper chips are actually built onto the motherboard. So if you actually fried one of these, it's either you're going to write off the board or you're going to have to get some hot air soldering and replace the chip. I could do it. Not everybody could necessarily do it though. You're going to pay a lot more money for this, but you're getting a lot more capability. And we will look at the difference in printing speeds between using the 8-bit controller and this full-blown 32-bit controller. For those of you on a budget, maybe you'll be okay with printing a little bit slower and using the lower cost Ramps board. And this has been true, and this is a true tested board over the years, and everybody uses it. It's not like you're getting something that's not going to work properly. You're just, with a lot of modern printers, you may be hitting the limits of performance and things like that with it. But for most people, it's going to be okay. If you're looking for that extra edge and you're doing more complicated builds and you want to have Wi-Fi and everything else as well available to it, then an obvious option might be this ST Micro reference board that is ready to go. It will take 24 volts for the heated beds and things like that. It's got loads of I/O and everything else on it, and it's still open source software. They will provide you all the software, and they got the guides on how to compile it and load it if you want, and how to modify it. So lots of capabilities, and I think a very good board, and we'll find out more about that when we get to use it. When you come to extruders, there are many. These I went on Thingiverse and found a few. This one is from Tech2C that I printed that seems to work very well, and it's easy to mount on a 2020 extrusion, or you could just screw it onto a board, on the vertical board perhaps, or on the top of it easily enough. This particular extruder frame is from Prusa themselves. They have a multicolor capability now with the Prusa i3, and the one thing about the Prusa designs is they've all been made open source, so you can download them and print your own components for use when you build your own 3D printer. Now, of course, if you're building a 3D printer and you need to print 3D printed parts, it's like chicken and the egg, right? But you can order these online or go to a 3D print shop and get them to print them for you. So that is also an option. Some of the other parts that I've done is I've printed some brackets for the X, Y, and Z positioning for the motors and the linear rail shafts and things like that. And the reason I did this is because there are some, well, one, I have a 3D printer, so it's relatively easy for me to do, but because of the difference in the height of a stepper motor versus these brackets for the linear rails, I found it easier to just quickly design in Fusion 360 some of the mounts and get it so that the spacing and everything else is more consistent. But the things like the board, I just hand laid it out and drilled and tapped the board for mounting everything on. So even if you just had some of the standard brackets, it would still work just fine. When we do the Core XY, of course, it's going to be built using aluminum 2020 and 3030 extrusions, and those will be designed completely different, but I will be again providing all the 3D models for that. So I think the other thing as well is the heated bed on this one is a 24 volt heated bed at I think a couple of 100 watts. I'll verify that. And for the Core XY build, I have a silicone heated mat, which is actually 300 in one direction, but it's actually 12 inches, but in the other direction it's 14 inches. So we'll end up with a heated bed of about 300 by 350 when we do the Core XY one. And this heated bed is actually 750 watts and 720 watts, 120 volts. So this one would not be driven from either of the two controllers. We will have to use a solid state relay or something like that and create an interface from the controller to be able to turn this on and off. Both beds are going to need the addition of a temperature sensor as well, and we'll cover that too. So I think that's pretty much everything that's common to both of them, and I think I've described enough of this jumping between the two kinds of builds. Now let's go onto the computer and have a look at the design, and then we'll come back and look a little bit more about how this has been put together so that you can start building your own if you want to, or at least get some ideas of where you'd want to start. Okay, here we are at the computer, and we're looking at the design of the 3D printer that I've gotten to so far. It is not complete. I have completed the base. I have not completed yet the vertical parts. A lot of it is done, but if I just rotate it around a little bit, you'll see what I haven't got is things like the X gantry configured and the mounting options set up for these bearing blocks and things like that right now. So I don't need to have that in order to complete the base, but I've got it there started so that we can refer to it later on. So what I have in this design, if I just go through and show you a few things, let me just turn off the frame for a second, and actually I'll turn off the x-axis, and just so we don't, because the only thing we're really looking at is the base unit, okay, which is the y-axis. So what I have here is a build support plate. It's actually going to be made just out of 1/4-inch plywood and put on top of a couple of other pieces. If I actually zoom in here a little bit, you can see, let me just turn off the joints so that they're not annoying everybody. Okay. Looking from the bottom, we've got 3 pieces of plywood here. Now I've cut these on a laser cutter, but if you're accurate, you can cut them on just by hand or using a compound miter saw and things like that. If you've got a few basic tools and you're competent using them, then you should be able to do this. What is important for these, and there's a few design decisions I made as we went along, is that the holes are in the right places. The actual edge, this whole edge here could be wavy, but the holes for mounting the actual heated bed, the holes for mounting the bearing blocks and the lead screw holder, they're the ones that have to be accurate, because you want these two shafts to run parallel to each other. Actually all 3 shafts to run parallel to each other. The stepper motor here drives the center shaft with a lead screw. The outer 2 shafts just simply have linear bearings on them. These brackets at the end, these are standard brackets that you get from MasterCar, eBay, all over the place. Anywhere that typically sells the bearing shafts will also give you some variation of a clamp for the end of those shafts. Now I deliberately did not 3D print clamps. I used the ones that came with them, and the ones I got I'll provide links to in the description and stuff. The center shaft, which is connected to the stepper motor, also has a change it around a bit, also has a coupler here so that you can have some flexibility in alignment of the stepper motor with the shaft. If there is any offsets and things, it'll be compensated for hopefully by that. This is a threaded shaft. It's a lead screw, 8 start, and it's an 8mm diameter. All of these shafts are 8mm in diameter. The pillow block with the lead screw nut on it is, in my case, I 3D printed it because I didn't have one, but you can buy these off the shelf. And the lead screw nut is actually made out of brass, so it isn't an it is not an anti-backlash nut, but I'm going to just go with it right now because from a cost perspective it was very economical. There is a very, very slight amount of play. Now I haven't screwed up all these screws yet, so if I showed you right now, it'll be rattling around for a lot of other reasons, but we will look into that as we go through the design. If it's too much and it affects the printing, then of course we will switch out this shaft and lead screw with the threaded nut with a belt and pulley, or even maybe just replace this with an anti-backlash nut. You can buy some from Open Builds. You could, if you have a 3D printer, you could print one yourself, or you could make one out of a block of Delrin plastic or something like that. There's lots of ways to do it, but we'll look at that when the time comes. The brackets, these green parts at the ends here on the base, these are used for, I'm trying to rotate this thing so that we can see them better. There we go. So these brackets I 3D printed. I designed them in Fusion 360 and printed them out on my 3D printer. They keep the spacing of these outer rails at exactly 200 millimeters apart. The two spaces, the two 3D printed parts are identical, which means that the shafts are all going to be parallel and in line with each other. The motor at this end that is mounted on this one, if you look at the designs of a stepper motor, you will see that the end of the stepper motor has exactly the same radius as some of the bearings that I've used. For instance, over here, if I can get back into it. Alright, this has got a rotational bearing here installed in here. This is exactly the same diameter. I deliberately picked it so that it fits in the same hole as the motor would at the other end, so I can use one bracket for both a stabilizer for the shaft and also for the motor mount. And what I haven't done yet is put a bracket on the outside of this to hold this in place. It is a very snug fit, but you really should have something screwed on the back of it to stop it from slowly pulling out as the motor moves over time. Now, you don't have to have this green 3D printed bracket. These clamps for the shafts could screw directly to a piece of wood. If I turn on the frame again for a second, you can see with the wood here I've got, I can screw straight through this into the wood, which is what I'm doing at the moment. We'll go look at that after I've gone through this. But if I didn't put that there, this is basically 4.5 millimeters thick. Now originally I did the bottom about 3 millimeters. It was just enough to maintain the spacing and a little bit of rigidity. And then I raised this another 1.5 millimeters that these clamps sit on. And the reason for that is because if you look at the design of a Nema 17 motor and look at where the center of the shaft of the motor is and compare it to the center of these, the center of these clamps is 20 millimeters above the bottom of the clamp. The center of a Nema 17 motor is 21.5 millimeters roughly above the center of the clamp. In fact, let's just go have a look at a Nema 17 diagram and we'll know for sure. One second. Yeah, so you can see from this diagram, I just pulled it up on the reprap.org website. The stepper motors, the Nema 17s, are 42.3, sort of, it depends on who you look at, but they're roughly 42.5-ish across. So the shaft is going to be 21 point something up from the mounting, on the edge of the mounting. So because the clamps that we were looking at here are 20 up, and this is 21.5 roughly, then you have to have a little bit of extra spacing. So what I've done is I've adjusted the holes on this bracket so that the motor, when it's mounted, is in exactly the same plane for its shaft as these two clamps at the end. And if we go back to the other side of this, you can see the shaft mounting. I don't know if I can get right in. There we go. You can see the holes of the stepper motor are lining up right with the holes on the plastic 3D printed part, and the shafts here are all in alignment. If they weren't, then my pillar blocks, which are trying to get a view for that now. Not so easy with everything here, but alright, you can see that this set of pillar blocks at the back, at the front, and the lead screw pill block holder are all at exactly the same level, and that's because these were doing the adjustment. If you didn't have the ability to 3D print something like this, then you could simply use the standard bracket that you can buy from numerous places to mount the stepper motor, or you could make one out of wood if you wanted to, and then put some spacers underneath these shaft brackets to lift it up about the 1.5 millimeters. You may need to sand it a little bit to get it more exact so that everything is perfectly smooth, but 1.5 millimeters is the size that I used, and that seems to work perfectly in this case. So if we just go back around, we'll just get this back to a better view and zoom in. Let's just turn the frame off again a second. So this top piece has just been cut out of plywood, the same as the two pieces underneath it. And as I said, the important thing for these is getting these holes perfectly aligned. So I'm going to make a diagram available, and if you're able to print it full size, then you could just lay it over a piece of wood and use it as a template to mark the holes. If you have access to something like a laser cutter, then you could just give it the step file. Sorry, not the step file. You can output a DXF and have it cut it out completely. Now, because I have access to a laser cutter, I actually did that myself, and it all fitted together perfectly. But if you're, even partly competent and you can drill accurate holes, then there's nothing to stop you just laying the template down on top of the wood and drilling through it by hand. It will work just as well. The critical thing is really the alignment of these shafts, because even if your piece of wood here is slightly askew, the critical aspect of the whole 3D printer is that the y-axis is exactly at right angles to the x-axis, and that's exactly at right angles or perpendicular to the z-axis going up and down. That way everything will run smoothly, and your square bricks that you might 3D print will actually be square. Now, the other design consideration I did here was what size of build platform did I want to create. So I decided that I already had a printer that was about 250 by 150 by about 150-ish, and I wanted something bigger than that. I wanted it to be big enough so that I could print something full scale, for instance, a head. And I know that I've got a couple of projects where I want to print a mask that my daughter's going to wear, which is going to be based on a skull. So I wanted something that's going to be capable of potentially printing something that big. So I went with a 300 by 300 print bed, and the heated bed that I got is several hundred watts, so it should heat up fairly quickly. The details of the Core XY printer that we're going to make, I will leave that till we start talking about the Core XY, but its build platform is going to be roughly the same size as this. I just may make it a bit taller, but the X and Y coordinate size of it will be about the same, about 300 by 300, maybe a bit bigger, depending on what I use for heating it and various other things. So where are we at with this now? So what you're looking at right now is a Prusa i3 MKII. This is basically the inspiration for the printer that I wanted to build, at least the lower cost one anyway. And you can see here that this has got a great big block of orange plastic on its build platform, and this is actually the build volume. This is a rather novel way of showing you how big an item this thing can print. Now, the actual Prusa i3 MKII is not the same build volume as what I would like to print. I think this one, let's see if we can see it here somewhere. So it's 25 centimeters, so 250 by 210 by 20 high. So that's not too bad a size. It's certainly a lot bigger than the one I have, but I wanted to go even bigger than that. So I've based my design on the Prusa i3, but I have not copied it. And one of the things that you will see, I'm trying to see if I can get to another diagram that better shows it, this one, is all of these orange parts that you can see on here are all 3D printed pieces. Okay, so there's quite a few on the Prusa i3, but the Prusa i3, you can get it in a metal frame, which is I think what this one is. It uses bolts and threaded rods and things like that to construct a lot of the frame. I wanted to minimize how many things I had to go out and buy to build the one I'm doing. So what I've used is a wooden frame for this, and I've also mounted it on a wooden base, and I've got the slide rails and things fit to that as well. Theoretically, as long as you're accurate with your drilling, there should be minimal setup in having to adjust anything. On the Prusa i3 MKII, it's if you're fairly skilled at assembling things, it's not too bad a printer to put together. I've never personally done it yet because I haven't had access to one, but you do have some potentially finicky things in adjusting the bolts on the threaded rods that construct the y-axis at the bottom here in order to get things square and stuff like that. So if you're not too adept at that kind of thing, then maybe my approach might be better. It might not, depends on what skills you have, or buying a complete kit of maybe a slightly different type. But the Prusa i3 is these days a benchmark printer in the market, and it is very good for its price. I'm trying to build one that's going to be a little bit less money than this, but that's why I'm pretty much doing everything from scratch. I will borrow some inspiration from Joseph Prusa with some of his parts. He has kindly made all of these 3D printable parts completely open source, so there's no problem if I download some of the models and actually print them. And one of the things that I will be doing is probably using a variation of his extruder and hot end assemblies for the printers as well. So you can see here, this printer itself is actually $900 US. The one we're going to build is hopefully only maybe $200 or $300. And yes, you can buy some from eBay, Banggood, etc. for that price as a kit, but I'm hoping that the one I'm going to build is even better. But we'll see. Once it's built and we do some testing, then we'll be able to judge as to whether it is actually a better printer or not than what you could buy as a kit. So going back to our design here, you can see the basic mechanics of this is pretty much the same. If I just hide the platforms, where are they? There we go. Okay, so now you can see better the design of this piece of it. It's actually very, very simple. And even if I put the frame back on, you can see how it sits on the frame. All right. This piece of wood would just be glued, and I haven't figured out how we're going to mount it on here yet, but I'm probably going to have some brackets on the side here at right angles to give it some support, maybe down the back so it's not in the way. But the basic design, as you can see, is very much like the Prusa i3 MKII, but I've designed this myself and I've scaled it to suit a 300 by 300 build volume. So anyway, I just want to cover in this video the base part. That's all I've got built right now. I'm still designing the other pieces. So I wanted to get something out so you guys can start thinking about it. So let's go back to the video camera and have a look. I'll disassemble part of the base so that you can see how it goes together, and then that'll complete this first part of the video. As I said, it is partially sponsored, so a lot of my components, screws, motors, electronics, power supplies and things are coming from RS Components. But from your perspective, if you wanted to build the most economical version, and we will find out whether there are any issues in quality as we go through, then I will provide links to Banggood and that for the components. So let's get back to the actual part that I've constructed so far, and we'll just have a little bit of a closer look. Okay, we're back at the bench in front of the 3D printer that we're building, and what I'm showing you here right now is a few of the components and pieces that I've been looking at that will be included in the build as we go. Now, the first thing I want to show is just this is an earlier iteration of that big green bracket, which is now white on here, holding the stepper motor and the threaded rods. This one was only 100 millimeter pitch on it between the two sides. I wanted to increase that to 200 so that there was more stability on the bed. So that's why I redesigned it, and I left the original mounting holes too, so that if you actually end up using this model to print yourself, you can have a choice about mounting it at 100 width or 200 width, whichever you prefer. So these will be made available. I've also modified it such that we don't have all this back overhang. One of my thoughts was that an option would be to use 2020 extrusions that you can get from RS Components and other places, and actually mount this directly onto an aluminum extrusion, which will be a very rigid base, and you wouldn't have to be getting big sheets of plywood or anything else. That's another option that maybe we'll have a look at once we've built the first design of this. We'll look at some alternative ways of building it, and we will be using a lot of aluminum extrusions too when we build the Core XY build. Anyway, so that was one of the axes mounting plates that I had done originally. This is a close-up of the part that I printed for holding the lead screw nut, and as you can see, it's very much the same as a standard 8mm pillar block for a linear rail mount. You'd have linear bearings inside, and this is dimensionally exactly the same as the ones that you get when you buy the shafts from Banggood and places like that. The holes in here are to accommodate the lead screw nut, and it allows me to position it in any orientation rotationally on here. If you mounted maybe two of them, one on each side, it might even allow you to potentially take out any of the backlash or something like that. But dealing with the backlash is going to be the subject of a later video. So that's the lead screw nut. Some of these other parts that are down here, for instance this, we will be going more in detail later, but this is a version of Joseph Prusa's Extruder Assembly. So this is actually for a dual extruder, and these are just the spring brackets, but I don't have all the parts to be able to assemble this yet. I need some different size bearings and things like that, but I did print one out to have a look at it, and it's actually a very nice design, printed without any support material or anything, so that's pretty good. But it's quite complicated. You're not going to manufacture that easily out of a piece of wood, but fortunately, if you do want to build your own printer and you're not buying an extrusion kit complete, which you can actually do, so that's not an issue if you don't have access to this, you can get these kind of things ordered online from a lot of 3D print shops that are available. So this one I printed myself just to see what it was like, and that's pretty good. This is the one I'm going to end up using to start with. I've actually just put it onto a motor so we can look at it. It uses a hobbed gear and a bearing, so this is very, very simple. And then a spring here just to push this bearing onto the hobbed gear with the filament in the middle, and then you've got a stepper motor to drive it. Very simple design, and this one is from, I think, Tech2C. I'll provide links to his site and things as well. So he also provided all of his 3D models for people to reuse for their own use as well. So that's what I've got for my extruder. This one is for the hot end, which we're going to have to get to eventually, and your hot end will mount in here. This is so that you can have a fan to come down and cool your part while you're printing it to give you better quality product at the end of it. This one as well is from Tech2C. Now I'm not sure if I'm going to use this one exactly as is yet, but I wanted to print it out and play with it to see how it went together, and also I like, visually I like to get a better idea of how I want to modify things. So having it held in my hands, feeling the weight of it, seeing how it mounts and things like that can give me a lot of ideas on how I might want to do my own. But anyway, this one is also from Tech2C, and I'll provide links to that too. Now, back to the actual the base. Raspberry Pi 3 I'm going to use for running Octoprint, so that's a way of managing the 3D printing process, as well as having the movement of, let's zoom out here, there we go. So as well as having the movement forward and backward of the bed, you also need to have some kind of limit switch detection. Well, ultimately you don't have to, but it's wise to have. So these are some very, very economical micro switch based switches that you can just mount somewhere. Haven't decided how I'm going to mount these yet, and then they would just feed via a cable. They come with a cable, quite a length of cable too, as you can see, to go back to the controller, so that the controller knows when it does a home, it can do an automatic home, trips the micro switch and stops moving in that direction and sets its 0 position. So I have a bunch of these too to use in this particular version of the project. We may use more advanced kind of sensors for the Core XY build, but we'll deal with that when we get to it. So let's get back to this. Let me just take this apart a little bit and then we'll continue the videoing. Okay, so here's the basic bed disassembled. What I have is basically a 530 by 530 piece of 3/4 inch thick plywood. Now I happen to have a partial sheet of marine ply in the garage, so I've just used that, which it's got more plies in it, but pretty much any nice plywood would be fine from your local hardware store. 3/4 of an inch thick in this dimensions, it's going to be very, very stable, so you shouldn't have to worry about anything moving. These are the standard linear rails, 8mm. They're not, there is some flex in them. You can see here, I don't know if you can see here or not, but as I'm flexing this, you can see I am able to push and make them slightly bend. But if you consider the fact that when you're 3D printing, first of all, your bearing blocks are going to be spaced slightly apart. The weight of the job that you're printing is going to be very, very minimal. So even though I can physically make these bend slightly, all of them, they shouldn't be an issue when you're actually trying to 3D print anything, right? And the nice thing is that the linear rails move very nicely. A little bit of noise to them, and we will be looking at using maybe some IGUS Delrin bearings at some point. But as I said, this is based on trying to do an economical build, and the Delrin bearings would be slightly more expensive. These are the two brackets. So this is the one at the front here with the bearing in it, and this is just, as you can see, rotational axis here, and the bearing just rotates in the mount. It's a very, very snug fit, so there's nothing going to be moving. You just need a plate to just if you wanted a bit of extra surety that it's not going to fall out over time. Just zooming back out again a little bit. So the pillar blocks, these sliding blocks are standard blocks. I actually got the diagrams for Fusion 360 straight from Master Car catalog. You can actually link and pull them in directly from within Fusion 360 to Master Car, which is absolutely great. They don't have everything on Master Car from a 3D model perspective, but they do have a lot of things. These mounting blocks at the end here, I actually had to draw those up myself, but they're just very, very simple shapes, so it was easy to do. I didn't have an actual coupler at the time, so I just quickly 3D printed one of the readily available ones off of the Thingiverse as well. But again, this is easy to buy. It's just that where I live takes about 60 days for anything to arrive, and I didn't want to wait another 60 days for these to get here. I had ordered some, but the supplier let me down and ended up canceling the order and refunding my money. So now I have to go and reorder them. So for now, I just printed a plastic one, just so that I can get on with the build. It should be fine, at least to start with anyway. So the next bit that I did here is I used some 1/4 inch birch plywood. This is fairly economical stuff that you can get from most hardware stores, and I printed 2 spaces. The reason for this is if I show you this base on here and I just mount it flat on top of this surface, if I just come down a bit, you can see that when it slides forward it hits this, and you can't avoid it because at this end, at the motor end, there we go, at the motor end, even if you made the plastic lower, you can see here that the screws for the motor and the motor itself are also higher than this platform. So no matter what you do with these mounting brackets, all right, for these here, whether you have them on spacers or not, even if you mount them straight to the wood, which is an alternative, and then you could just have a standalone motor mount and things for this. You would still need to space them to get the bearings, the shaft, sorry, all at the same height. You would have a little harder time aligning them in a nice straight line, but you won't get over the fact that your main support platform has to get over the top of the motor. So what I did was, using the exact same hole pattern and the full width, I minimally created these two templates so that it will space it up enough to get the main build support platform over the top of this, and that's exactly what they do. So this is basically a 1/2 inch of rise up on there, and that gives it just enough clearance now over the top of this bracket so that the build platform support can come way out the front here. All right. The reason I've got these two notches cut in here is because when we go at the other end, the spindle, the coupling here is actually just high enough to hit the wood. If I take this here, right, you can see it hits it. So I put a small notch in there just so that I can get this to move all the way to the end. And I kept the thickness of this wood to only what I require for mounting these two pill blocks right to the edge of them, so that I actually maximize the distance to these mounting blocks so that they all hit at the same time. And that's pretty much what I've done there. So from an assembly perspective, if you leave all these parts loose, and I've got them loose at the moment, there is a risk that they can potentially move around, because there's like 3/4 inch of screw thread sticking up out of the hole too when you're screwing it down. So I would suggest that you glue these pieces together when you assemble it. Maybe use the screws to go through to clamp it where it matters, to make sure you're fully perfectly aligned. But if you clamp it all together, it's going to make for a much more solid platform. The screws are all, in this case, M4, I think, M4, yes, for mounting into all of these sliding rail blocks. And these come with, and unfortunately, if you're in Canada, it kind of sucks a little bit, but everything in this build is metric, and you'll find that all of these pieces that you order, the extrusions, these rails and bearings and everything else, they're all metric sizes. So it's something you need to get used to, and you may have to shop around a little bit to get the sufficient supply of the metric nuts and things. You can buy them from RS Components if you're watching this from Europe, or you can get them from some of the more industrial supply shops and things like that too. All of mine were provided to me from RS Components as a sponsor for this build, so it saved me a lot of shopping around. Certainly here in Canada, metric screws are not the norm. They're still using imperial for whatever reason. Anyway, that's the base. So I'm going to put this back together now. I'm going to glue these pieces, these three sets together, so that they make for a more solid mount. The only other thing I will mention, which is something I didn't realize quite at the time, is I got a lot of screws, and I went at 10 millimeter, 20 millimeter, 30 millimeter, 40 millimeter, etc. But in some cases, when you look at what's threaded, these don't thread in very far. They barely go in 5 millimeters before they run out of threaded space. Now I could increase the depth of the thread. I have some taps out in the garage, but you may want to go for some of the 25 and 35 millimeter as well, so that they'll fit better. So this one itself right now is, well actually this one is 25 millimeter, and I think 20 millimeter is a bit too short for this, because each of these is 6. So 6, 6, and 6, 3 6s are 18. Yeah, so 18 millimeters. So 20 millimeters would only leave 2 millimeters on here once you've got all three pieces of wood stacked up. So you may have to file a little bit off or deepen the holes. It just depends on how thick your wood ends up being. So you'll have to judge that at the time when you make it yourself. Now, you don't necessarily have to go full width with this. The reason I've done is because I've mounted right through, and it's providing a lot more support for the main mounting plate on here, because I just basically drilled the holes for the heated plate, which is this one. It's a 300 by 300 heated plate, that's then able to go straight on top and have the springs in the corners for adjusting and leveling the bed. This bed itself is a 24 volt one. You can get 12 volt ones, but if you're going up to a bed this size, you're going to have a very big power supply and very big wires to connect the bed to the power supply through the controller. A lot of controllers also won't handle the amount of current you need if you're running off of 12 volts for the heated bed, so I went with the 24 volt one here. So that means that my wires can be a lot thinner, and when you're talking about the fact that this is a moving component, then you really don't want to have really stiff wires here, because they're going to, one, be stressed with the continuous movement, and two, they're going to be adding an increased load against the motors and things, so you do run the risk of skipping steps and things like that the more load you put on it. Anyway, the last thing I want to do is show you the backlash. Trying to lost the word there for a second. So here's the bed reassembled and tightened down. I haven't put the heated bed on it, but you can see that everything else is assembled. What I've done is I've used some washers just to, one, spread the load of the smaller screws on the wood so it doesn't crush it, and also because they, as I said, the length of the screws can be critical depending on the thickness of your wood. Adding these washers is just enough so that I'm not bottoming out on the mounting blocks underneath, so I can get it nice and solid. Now what you can now hear, and if I'm going to zoom in on just one end so that you can maybe see it better. Yeah, it's probably like 0.1 or less of a millimeter. So in the scheme of things for what we're doing, considering we're going to be using, say, a 0.4 millimeter nozzle and things like that, this may be negligible, but we will look, if it proves to be an issue, at improving that at a later date. But for now, that is the main bed assembled, and let me just zoom back out again, and I'll just show you the heated bed and what that takes to put on. So the heated bed, what it does is you use screws and springs like these ones, and you have one on each of the four corners that the heated bed would then be suspended. So if on the heated bed here you can see these holes, they're M3 size, so I've drilled some M3 clearance holes on the corner of my support platform, and this would then be suspended on the springs. Now what you've got is basically you'd have an M3 screw, the spring running through it. Now remember, this is on top of the aluminum. This is between the aluminum base plate and the support plate, and then this would go through the support plate, and there would be a nut on the bottom, maybe a washer just to spread the load and stop any wear, and that would then create a nice adjustable spring-loaded corner mount for the build plate. So I'm going to just put those on, and then I'll come back to you again. So here's the heated bed reattached to the platform, and here's a close-up of one of the corners so you can see how it's mounted. So you can see you got the screw through the build platform, through a spring, through the base platform, and then a nut on the bottom. So all you have to do is you just have to screw down or not, or loosen up the nut, and you can see you can actually have quite a range of adjustment on this as you want, so that you can get the bed as level as possible. Now a lot of software that you use for 3D printers these days will actually have built-in auto bed leveling, where it would probe various places on the bed and measure where it touches or where it gets close to touching. And what we're going to use for this build is I've actually got an inductive sensor that should be able to pick up the metal build plate when it gets close to it without touching it. So we'll give that a try. If I put a piece of glass on top of here as the actual build surface, then that might inhibit it from sensing properly. We may have to look at an alternative method for that. Worst case comes to worst, we just use the paper method, which is where you manually bring the heated nozzle down. Where's my nozzle? I've got one around here somewhere. So whilst I don't have the nozzle actually on the axis right now, this is actually an E3D clone nozzle and hot end. And the filament would come down here, be squeezed through here. This is heated up to a few hundred degrees centigrade if necessary, and squeezes out of a really little nozzle down here. But when you when you're zeroing the bed, you would bring it down until you can get a piece of paper just touching underneath, and then that would be your 0 point. So that would be the manual process. If you're doing it with automatic bed leveling, you'd have some kind of sensor that would move up and down with the head, and would then set the 0 when it detected the presence of the bed or whatever it's looking for in that case. But I have 2 of these nozzles, one for each printer that we're going to be building. I don't know how well they're going to work. From what I've seen on other channels, they do seem to work quite well, although nothing beats a genuine E3D head or something like that. But again, budget, we're looking at how cheaply we can build a printer within reason. So we're going to just stick with this one for now and see how well it produces prints. That's it for this first part of the video anyway. It's already probably getting on quite a ways, and I don't want to make it too long. So I will see you in the next part. The next part of the video for this printer will probably be the construction of the Z-axis and the X-axis. And once we've got that done, we'll start looking at the various pieces of electronics, limit switches, etc., etc. So, see you next time. Hope you enjoyed the video. If you did, give it a thumbs up, click a like, whatever it is, and subscribe and look out for the next ones in the series. Bye.